Hey, welcome everybody. So, my name is Matt, and I'm recording a secret special message for all of you. It's about jet engines and some of the really cool material science that goes into them. So, I'm going to send this secret message into the future. Don't be alarmed, but you are all from the future, and you'll get my secret message. But why? Why am I doing this? Well, the purpose of this presentation is, well, one, because material science is in your curriculum, so you got to learn this stuff. But also, jets are really cool, and some of the material science that goes into them is really cool. And if you don't believe me, I mean, just look at my title slide here. This is the SR-71 Blackbird, and it's like shooting fire out of its jet engines. This is still the fastest air-breathing plane ever piloted, and in fact, it was so fast that this was a reconnaissance plane. It would fly over enemy territory to take photos and such. And the protocol, if it was ever shot at by missiles and the like, was just to hit the gas and fly so fast that none of the missiles could ever catch them. And none of them were ever shot down. Still the fastest airplane ever piloted by a human. Pretty impressive stuff, and some pretty impressive material science that goes into jet engines that we're going to talk about. Change the slide. Okay, so I talked about jet engines, but what are they? Let's see if I have a pointer. I do. Okay, so they're not the thing in the middle, but these things, let's count them. 1, 2, 3, and 4. So cars move on the ground by pushing off of the road, the earth. Believe it or not, planes fly in the air, so they can't push off the ground. So how do they move forward? Well, they push off of the air, and the jet engine's job is to push air back really fast, and that pushes the plane forward. But I hear you asking from the future, just how fast the jet engines push the air backwards? And I think that we should do an experiment. So let's maybe put a car behind a jet engine and see what happens. See if my video will play. Okay, so that was a lot of fun. Yeah, so that's what jet engines do. They push air back. This is also a jet engine inside this plane. This is the F-35 fighter jet, and I like this one. I work for a company called Howmet Aerospace, and the parts I work on are actually in the core of this engine. So I get to work firsthand with a lot of this material science stuff, which is why I'm making a presentation on it. Here's another engine that I've worked on a fair bit. This is the Rolls-Royce Trent engine, and this goes on planes that you or I might fly on a normal day. I'm assuming that none of you are piloting fighter jets just yet. But yeah, so basically you'll notice this is the jet engine, right? And basically out front, you just have like a big fan that spins around and pushes air backwards. And you can imagine like a fan that you sit on your bedstand just plugs into the wall, and that's what powers the thing that spins the air and pushes it. But planes, again, fly in the air, and you can't just plug this big fan into the wall outlet when you're 30,000 feet up off the ground. So the planes have to make that power while they're at altitude, and that's really what the jet engines are for. The jet engine, the core of it, the part with the cool material science that we're going to talk about, is actually behind this big fan. Let's look at a cross section of this engine. So basically looking at it like this picture on the left, but we're just going to cut the thing in half. Yeah, so out front you have the big fan, and then behind it you have fans and fans and fans and fans. You just have a whole bunch of rows of fans, and what they do is they take the air and they compress it and they squeeze it and they heat it up. So you got this compressed, squeezed air all squished together. You add jet fuel into it, and boom, you light it up. You explode it. So you can imagine exploding it pushes the air out really, really fast, which is exactly what you want. But you can actually make the whole thing more efficient by harnessing some of the power of that explosion and using it to spin a fan. So out front, you have fans pushing stuff in. After the explosion, you have turbines, which are kind of like fans in reverse. Fans use energy to make air go fast or compress it, and turbines take fast moving air, like the air right behind the explosion, and they turn it into rotational energy, which powers our fan, which is really what pushes the whole plane forward. And the cool material science, the coolest material science in my opinion, happens right behind the explosion in these high pressure turbine vanes. That is what I get to work on every day, and it's really cool. So let's talk a little bit more about the material science that goes into making these high pressure turbine blades that survive right behind a constant explosion. Yeah, so it's really the high pressure turbine is doing the same thing as like a windmill, right? It's taking moving air and turning it into rotational energy. It's just where a windmill might take a nice gentle breeze and turn that into electricity. Jet engine, high pressure turbine, takes the power of compressed exploding air and turns that into rotational motion that powers a bigger fan. Right, so this is a jet engine with full afterburner. And while we're looking at this, keep in mind that the parts we're talking about, they're buried up in like the heart of the engine. I'll use my laser pointer right here. They got to survive like up here. So I want you to start to think about, let's say you're a material scientist, what are you going to make these high pressure turbine blades out of so that they can survive inside this chamber here, inside this jet engine? And with that in mind, let's meet some materials. So here's how this is going to work. I'm going to introduce you to a couple different materials, and we will analyze what might make them good for use in the application of a jet turbine, and what maybe some characteristics are of different materials that won't work in a jet turbine. So I'm going to introduce you to 8 different materials, and I want you to pick one or 2 or however many you want. Maybe pick one, it'll be more fun that way. that you think, pick one that you think is a good choice to make a turbine blade out of. We'll look at the most important material properties, and then we'll come to a conclusion on which one is actually the best, and which one gets used in industry today to make high pressure turbine blades. So we have ice. Maybe you want to make your blades out of ice. We have plastic, lots of stuff made out of plastic, bottles, aluminum, that's a good one, strong, lightweight metal. We have glass, borosilicate glass, it's like a fancy glass used for lab equipment. We have stainless steel, pots, pans, and a myriad of other applications as well, all over industry. You have CMS X7 superalloy, which is used in, among other things, like turbochargers for your car. You have zirconium dioxide, which is what we call a ceramic. Ceramics are, the ceramic you're probably most familiar with is porcelain. It's what toilet bowls are made out of. But ceramics have some cool properties we'll talk about. Zirconium dioxide is just a fancy ceramic. And we have our final material here is tungsten, which is a metal used in light bulbs, among other things. So those are our 8 materials. I want you to look and pick one that you think will be best. And maybe, you know, when you're picking your material, let's talk about what material properties are important, right? So I've shown you a couple pictures of jet engines, and a lot of them have fire coming out of them. So maybe what would be an important material property? Maybe this material, whatever it is, needs to survive being really hot. So just how hot, right? Well, a hot day is like 100 degrees. Baking pizza is like 400 degrees. Red hot iron, 1500 degrees. Now we're getting really hot. Melting point of steel is like 2500. And a jet engine finally is at like 3000 degrees. That is really, really hot. So our material needs to be able to survive in that kind of environment. So I'm thinking of the materials that I gave you on the previous couple slides. I hope none of you picked ice, because I don't know if that one's going to hold up to 3000 degrees. Let's look at how some of the different materials stack up here. We're going to look at their melting points. So, you know, at a minimum, you'd hope that these materials would be able to not melt in the environment that they operate in. And, yep, ice, not looking so good, melts at 32. And tungsten, holy cow, that's like over 6,000 degrees Fahrenheit to get that to melt. That's incredible. And actually, all of these are doing okay. I know the scale makes them look a lot smaller than like tungsten, but like even aluminum is 1200 degrees. The superalloy and stainless steel are both over 2000 degrees. They're getting close. And the ceramic, the zirconium dioxide, is really high as well. But yeah, so I'm going to score each of the materials we talked about based on my not quite scientific but directionally correct understanding of how suitable they are for that material characteristic. So for example, tungsten gets a 10 out of 10 because it can handle 3000 degrees with ease. Ice, not so much. So let's have a quick sidebar here, because I talked about tungsten, and tungsten's actually my favorite element. I mean, like, just look at it, right? It's like, it looks like something that you make the Infinity Gauntlet out of, or it has like these cool futuristic crystals on it. Its chemical symbol is W, which stands for wolfram, which is just kind of weird and awesome. Yeah, it's super cool. And one of the things that tungsten gets used for is in kind of old-fashioned light bulbs. Yeah, so you see, this is an old-fashioned incandescent light bulb, And the center here, this filament, is made out of tungsten. You pass electricity through it, and the tungsten filament starts to glow white hot. And it's used for this because it can get really, really hot without melting. But, I wonder, there is something about this that worries me for the prospects of using tungsten in a jet engine. You see how in a light bulb we put the glass around the tungsten filament? Why would we do that? Now you might think, okay, that's to protect some bumbo like myself from being clumsy and knocking into it and burning myself on the white hot tungsten filament, and you'd be partly right, but that's not actually the main reason that we have to put glass around tungsten filaments when we use them in light bulbs. So what the glass does is keep oxygen away from this really hot tungsten. And the reason we have to do that is something called corrosion. So corrosion, what is corrosion? Well, corrosion is basically like rusting. I'm sure you've all seen metals rust before, where over time the environment, in particular like the oxygen and sulfur in an environment, react with the material, and it can cause it to kind of fall apart. So when you see like old cars sitting around that are rusting apart, I mean that's what happened to them. They got attacked by the environment. Certain materials are a lot better at withstanding corrosion than others, and unfortunately tungsten is not particularly good at withstanding corrosion, at least not at the temperatures that we need it to operate at on the inside of a jet engine. So with corrosion in mind, let's update our scoreboard. Oh, you can see, so the ceramics, one of their interesting properties is they're actually really good at resisting corrosion. They've basically already been rusted. They've already been attacked by oxygen. They're going to react. They're already as corroded as they're ever going to be. So we don't need to worry about them degrading when they get corroded more. They can't corrode more. Tungsten, unfortunately, doesn't do so well, but a lot of our other ones are at least doing okay in terms of corrosion resistance. But I'm looking now at our scoreboard, and we have temperature, which we talked about, needs to be temperature resistant to operate inside a jet engine. Also needs to be corrosion resistant. And up at the top of the scoreboard so far, we have glass, which I don't know. Is glass going to be a good material to put inside of a jet engine? I mean, what could go wrong, right? Well, you might know if you've thrown a baseball that didn't go quite where you intended it, that glass is not particularly tough. It can actually shatter and explode. It doesn't take a lot of energy to break it. So let's talk about another material property, toughness. So toughness is the ability of a material to withstand shock loading without fracture. So materials that are very tough generally are hard, but they're also, and then this is important, they're also, when something's tough, it's bendy. To actually break something like a lot of metals and glass takes the same amount of force, but the thing is, when you deform a metal, it just kind of dents a little bit, whereas something like glass will catastrophically fracture and break into pieces. So ductility is like how bendy something is. It helps actually be a little bit bendy because then you can absorb some energy when something bad happens. But, is this really an important property for jet engines? Like, what could go wrong inside of a jet engine where it's going to get, your turbine blade's going to get whacked by something? That's what the chicken's wondering. So let's watch another quick video here.
Yes, what you saw was a chicken being thrown inside an aircraft engine. This shocking video shows one of the many tests aircraft engines must undergo before they're used on an aircraft. Although throwing chicken inside an engine might sound shocking, wait until you see what 800 gallons of water can do to an engine. But why are the...
All right. We don't need to watch it again. Okay, so let's update our scoreboard with toughness in mind. So our metals, like stainless steel, superalloy, and aluminum, actually do pretty well with toughness. They can bend a little bit to help absorb some energy when something catastrophic comes their way. Stuff like ceramics and glass they're not very tough materials. They tend to fracture and break apart, which makes them unfortunately unsuitable for jet engine applications where you need to be able to withstand lots of vibrations and maybe even the occasional chicken coming through the blades. So we've looked at temperature, corrosion, toughness so far. Is there any other material property that might be important for being and surviving inside of a jet engine as a rotating turbine blade? Let's, while you think about that question, let's watch another video. And this is a CD getting spun really, really fast. So what's going to happen when you spin something really, really fast? Let's watch.
Okay, here we have a CD connected to a vacuum motor, spinning about 30,000 RPM.
Okay, wow. So the edge of that CD was spinning at over 300 miles an hour when it blew apart. How fast did jet engines spin? So here's just a speed comparison. A car on the highway might go like 70 miles an hour if you're following the speed limit. A wind turbine, they actually spin pretty fast. The tip of them goes at 150 miles an hour, very fast. The CD exploded like we just saw at about 300 miles an hour. A plane moves through the air. This isn't the engine, but the plane itself moves at about 500 miles an hour. And finally, our jet engine, at the tip of those fan blades, they need to be able to rotate at 870 miles an hour. That's really, really fast. And the challenge that this introduces for material scientists trying to pick a material to spin that fast is that materials tend to want to explode, fly apart when you spin them really fast. It's why that if you're ever on like a merry-go-round, you feel forced to the outside, you want to fly apart. So the material, whichever one we choose, needs to be able to hold itself together well. Basically, it needs to be really strong to not explode like that CD we just watched. So this is a material property that we call tensile strength, and it's basically how much force it takes to pull a material apart. So here are all of our materials, and their tensile strength is plotted out. And oh man, look at tungsten again. It's really too bad that it corrodes at high temperatures, because it would make a great material otherwise. So let's ignore that, and let's just focus on our next two strongest materials, and I actually want to zoom in on those. We're going to look at them. So our next two strongest materials are nickel superalloy and stainless steel, and it looks like stainless steel is a little bit stronger. So yeah, that's awesome. Let's use that for our jet engines. But you know, I don't know, I have like a nagging feeling. Did I make a mistake? I don't know. Do you see anything? Tensile strength, PSI, pounds per square second. Tensile strength at room temperature, stainless steel, I don't know. What's my mistake? I know what it is. Okay, so this is tensile strength at room temperature. Our materials, if we're using them inside a jet engine that's up to 3,000 degrees, they're not at room temperature. They're very, very hot. So we don't want to look at tensile strength at room temperature. We want to look at tensile strength closer to the temperature range that these materials actually operate at. Ooh, wow, that's a big difference. Okay, so the first chart was tensile strength at room temperature. This one is tensile strength at 1,500 degrees Fahrenheit, which is closer to what the fan blades are actually going to operate at inside an engine. And you can see that stainless steel, it was stronger at room temperature, but it loses almost all of its strength when you go up to 1,500 degrees Fahrenheit. Whereas nickel superalloy actually goes, it's a little bit stronger when you get it that hot. And that's weird. It's actually very unusual. What stainless steel is doing is very common among materials. When you heat stuff up really, really, really hot, it tends to get kind of Play-Doh-y, and it can stretch out, and it doesn't want to, it's not as strong anymore. Superalloys are called superalloys because they're one of a very select group of materials that actually, as they get hotter, they get stronger, and they can operate very close to their ultimate melting point, which is really cool. So yeah, let's update our scoreboard one more time, taking into account tensile strength. And looks like the nickel superalloy, CMS X7, SS7, is on top with 31 points. So what material do we use to make jet turbine blades? Well, modern jet turbine blades are usually made from nickel-based superalloys like CMS X7. That's the CMS X7 is a particular formulation of nickel superalloy. Yeah, so I'm thinking back though to you know, the one material property that superalloy wasn't the very top of the chart for was temperature resistance. We need to operate up to 3,000 degrees Fahrenheit, and nickel-based superalloys, even though they're very strong, close to their melting point, they will melt eventually, and they melt under 3,000 degrees Fahrenheit. So is there anything we could do to try to prevent that? I wonder. Well, you might remember that our toilet bowl material, the ceramic, was very good for corrosion resistance. It was very good at temperature resistance. The only problem was that it tended to shatter a little bit. It wasn't particularly tough. But why don't we let the nickel superalloy be the backbone of our blade, and we'll just cover it with a thin coating of the zirconium dioxide, the ceramic toilet bowl material that will help protect it from the extreme temperatures. And this is what's actually done in the hottest part of modern jet engines. You use the nickel superalloy as the core, and you might put some protective coatings on it that help with the temperature resistance. And yeah, here's a picture of them. This is what I make every day, and it's kind of fun to talk to you guys all about it. So that concludes my presentation, and you're from the future. I am sadly from the past, and I'm sending this presentation to you, which means that I can't actually answer any of your questions. So this is like a little bit awkward, but I have a fun game for us. So you have your teachers. I hope you have your teachers in the room with you. If you ask a question and about, material science in general or jet engines or whatever, and your teacher can answer it without having to look anything up, that's 1 point. Okay, if your teacher can answer your question, but they have to look it up first, that's 3 points. And if you can stump your teacher, I think that's a full 5 points, but only if the following day you have to look it up yourself. It's no fun just to ask your teacher really, really hard questions. I need you to ask them questions that they can't answer, but you can. Outsmart your teachers. Go ahead and look some of this stuff up about material science and jet engines. I think it's really cool, but I guess I'm a little bit biased. So anyway, that's all I got. I hope you guys are having a great day, and yeah, cheers, peace, bye.